if you've been following the sequence, no pun intended there, of videos, you'll notice that we're going to, when we use the previous example here to help us write the term, you'll see a nice tie between the graphing of it, making the table, and then leading us to the equation. So let's just record again the little smart chart we had developed in terms of N and AN. And so your past experience of using tables and graphs to lead you to equations, very helpful here. We have this common ratio happening each time, so it's important to now include the common ratio. That common ratio is 1/2. And now again, a nice tie back to exponential growth or decay functions will show up here. It should make sense that, and it's a little bit different, but it should make sense that if we have f of x equal to a times b to the x, it's a nice relationship now to how we actually write the nth term. And so if we were doing that, the nth term for this sequence, 12, 6, 3, 1.5, we would first identify the common ratio. We want to identify our first term or our initial value. So A1 in this case would be 12. And this is how it's different then. So when we raise it to its power, because of how sequences behave, we don't write it to the nth, we write it to the n minus 1. So all geometric sequence explicit formulas are of the form, it's very similar, but they're all of the form a sub n is equal to, we take our initial value in this case, a1, and we multiply that by the common ratio to the n minus 1. All of them follow this same patterning. Notice the relationship again between exponential growth and decay functions and then explicit equations for geometric sequences. So how would we write this first example from what we did in example 2? It would actually go, well, a sub n, the nth term, is going to be found by taking the first term. In this case, it's 12 times that common ratio, which is 1/2. So I would use parentheses here. Anytime you have, two numbers next to each other, just using the dot sometimes will lead to issues. So I'm just going to use parentheses there. And then this is to the n minus 1. So the nth term, or the formula, or the equation for this sequence 12, 6, 3, 1.5 is a sub n is equal to 12 times 1/2 to the n minus 1. You might wonder, well, how does that generate this sequence? And that's an important part of this. I'm going to demonstrate that actually in the writing of example 4, and then I'll show you we'll flesh it all the way out, how it actually, the equation itself will generate the sequence. That's an important part to this whole thing because I think it gets left behind within this section a little bit. So really you want to be able to generate sequences given their equations. So let's look at this. We've got 3, 9, 27. So our first job is to identify, well, what the first term is. That's pretty obvious. That's 3. And then now let's calculate to find the common ratio. So that common ratio is going to be, well, 27 divided by 9, or 9 divided by 3. We would use that to find out that what's also pretty obvious, that our common ratio is 3. So it just so happens our first term and our common ratio are the same number. Don't let that take away or mess you up in being able to write the formula. So we're going to write this as a sub n is equal to 3 times 3 to the n minus 1. Now here's why we use to the n minus 1. Because we already know the first term is 3, to find our second term, we're going to put in to the n value 2 because it's the second term. So here's how the equation will actually generate, as we say, the sequence. So let me clear some space here. Let's move this up. And so to test this equation, how does it really work? Well, we already know that the first term is 3. So the second term, we're going to put 2 in for n. That means find a sub 2. You're going to go 3. Use the formula. I'm just using the formula. 3 times 3 to the 2 goes in for n minus 1. And that math goes like this. 3 times 3 to the first power. 2 minus 1 is 1. Okay, so then we got 9. So sure enough, our first term being 3, we just found our second term. This is a sub 2. Second term, that's 9. So if we continue this, we can find the third term by putting in 3 for our function or our rule or the equation. Find the next term or the nth term. That's going to be 3 times 3 to the 3 minus 1. That math gives us 3 times 3 squared. 3 squared is 9. 9 times 3 gives us that 27. So sure enough, this formula right here, let's box it in. It was found from its first term, its common ratio, and then it actually generates the sequence. I would really encourage you to work back through this example on your own, generating or finding, deriving that equation. Practice this and make sure it matches with what you've seen here. Next video, we'll look at a variation of this same type of situation. It's just a little tweak. See you in the next video.